Hello guys, welcome to a new video in this video series of graphs and networks. Today we'll be discussing about Prim's algorithm for a minimum spanning tree. So in the previous video we had discussed about Kruskal's algorithm for finding a minimum spanning tree, and in this video we'll discuss another solution for the same minimum spanning tree problem, and that's called the Prim's algorithm. So to recall the MST problem, so given a connected PQ graph G which is also a weighted graph, find a spanning tree of the graph such that the weight is minimum. So the solution in this case is the Prim's algorithm. So this is a greedy algorithm, and let's see how it's implemented. So what your input is a connected weighted graph G. This is the vertex set capital V, edge set capital E, and the set of weights for each edge. Okay, and so before you start your algorithm, an important note is that all loops, that is a vertex from the same point to the same point, and parallel edges need to be removed. So parallel edges are basically two edges from the same starting and ending point. Okay, it can be more than two as well, but this is the most basic case. So any parallel edges and any loops, they need to be removed, okay, to proceed further with this algorithm. So your step one is initialization. So first of all, we initialize T with 5, that is your null set. So T will be your edge set in the final minimum spanning tree, and we initialize our weight, that is W of T, to 0, and we initialize a set called S with the vertex U. So U can be any arbitrary vertex in your graph. The reason for it being arbitrary is because since it will be a spanning tree, at one point of time that any vertex has to be covered, so it doesn't really matter which vertex you start off with. So just choose one arbitrary vertex and you can proceed. And your another set S star is the set of vertices V minus S. Okay, so your vertex set minus all the vertices present in your set S. Okay, so that's this is the initialization step. So step 2 is, while S star is not equal to null set, do the following steps. So we first of all find the edge with minimum weight in S comma S star. So this particular notation means that so this is basically the set of all U comma V, where U comma V is an edge, such that your U belongs to S and your V belongs to S star. So we're basically listing them down as a set of all the edges from all the vertices present in your set S to all the vertices present in your set S star. Okay, so that's what I've written here again. So find an edge E, U comma V, where U belongs to S and V belongs to S star. Now we find the minimum. So yeah, we find the edge with minimum weight. Then after finding the edge with minimum weight, we append our set T, our edge set T of our minimum spanning tree, as T changes to T union your new edge, and your S changes to S union your new edge, and S star as usual is your vertex set V minus the elements present in S, and your weight gets appended to W of T equal to W of T plus your weight of your new edge. Okay, so that's the do part. So we do all these steps until and unless our S star becomes our null set. Okay, and after you do all this, you have an output as a minimum spanning tree with weight W of T. Okay, so let's illustrate the Prim's algorithm with an example. So say you've got a graph G as illustrated here, and it has 6 points A, B, C, D, E, F, and you see that all the edges have been given a particular weight. It may or may not be the same, doesn't really matter. So first of all, as was step 1, we initialize T as our null set, that is basically 5. This is the same thing as 5. And S, I have taken point A. This is a totally arbitrary choice. You can take any other point as well. I just found A to be a good point to start. And so my S star would be my vertexes, that is A, B, C, D, E, F minus my set point A. So I'm left with B, C, D, E, F. Okay, and as always, weight of T is initialized to 0. Okay, so now I'll be going with my step 2, and I'll be explaining each iteration step by step. Okay, so first of all, my iteration 1, I see that my S is A and my S star is B, C, D, E, F. So S comma S star will be all the set of vertices from the points in S to the points in S star. So I've got point A in my set S and points B, C, D, E, F in my set S star. So the edges from A to all the possible edges starting from A to any of these points will come in this S comma S star set. So we see that A is connected to B and A is connected to C. So our S comma S star set will be the set of edges AB and AC. Now we find the edge with minimum weight. So we see that AB has a weight of 7 and AC has a weight of 8. So obviously edge AB is the minimum one. So I'm going to be appending my S to be my A plus my new point, that is B. Okay, and S star as a result would be C, D, E, F. My T would be T, that was the initial null set, union my new edge, that is AB. So null union AB is AB itself, and my weight becomes from 0 plus weight of AB, that is 7. So weight is 0 plus 7 equal to 7. So that's it with my iteration 1. So from this we move to iteration 2. So the S and S star of iteration 1 become the starting S and S star for iteration 2. So using this, S becomes AB and S star, okay, sorry about that, and S star will become C, D, E, F. Okay, so as again we collect the set of vertices, set of edges, my bad, from our set S to S star, and in this case it will be AC, BC and BD, because we have points A and B in our set S. Okay, so these are all the set of possible edges found connecting the points of S to the points of S star. And we see from this set, the set with minimum weight is BC, which has a weight of 3. So we find minimum as BC, then we append our point C to our set S and find S star as V minus S, append our edge BC to our set T, that is our edge set, and append our weight to 7 plus 3 equals 10. Similarly for iteration 3, now we have S as ABC, S star as DEF, that is basically just V minus S. Now again we write the set of edges from S to S star, that is BD, CD and CE, and the minimum weight of the edge among these is CE, as it has a weight of 3. So and then we append S to be A, B, C and E. Our S star becomes D comma F, and our T, that is our edge set, becomes AB, BC and C, and our weight gets appended to 10 plus 3 equals 13. So next up, iteration 4, we have S from our iteration 3 as ABCE and S star as D comma F. Now all the edges from S to S star include BD, CD, ED and EF. Now one thing to be noticed here is that the weights of ED, that is 2, and EF, that is again 2, are same. So when a case of when you occur any situation that has the same weights, you can choose arbitrarily. So it doesn't really matter, say I choose ED for example. So it doesn't really matter, so I'm choosing ED. You can break your ties arbitrarily. You could have also chosen EF, that doesn't matter, but I'm choosing ED. So that means my set S will be appended to ABCED. My S star will now only become F, and my edge set will be AB, BC, CE and ED, because I'm choosing ED. And my weight gets appended to 13, that was the existing weight, plus 2 weight of my new appended edge, that is ED. Okay, and iteration 5, my S would be ABCED, my S star is F. All the edges from S to S star are only 2, those are DF and EF. You can see only 2 edges are connected to F, and the minimum of these is EF. And so my S now would be ABCEDF. My S star is now the null set, because S is the same thing as B right here in this iteration, so S star becomes null. My T would be AB, BC, CE, ED and EF, and my weight is 15 plus 2, that is 17. Now we will not proceed to iteration 6, because our S star at this iteration is the null set. Okay, so that we won't proceed to our iteration 6. So at this point of time we're done. Okay, so since S star is equal to 5, we terminate our iterations, and therefore our final minimum spanning tree would be this edges of our. So first of all, we just draw the vertices of our graph, then we connect the edges present in our set T. So we have something that looks like this. This is our minimum spanning tree, and its weight can be calculated by just adding the weights of the corresponding edges in your minimum spanning tree. So yeah, that's how you calculate your weight. So that was Prim's algorithm implementation with an example. So the next thing is the time complexity of this particular algorithm. So the worst case time complexity is order of q log p, where q is your number of edges and p is your number of vertices. Similarly, it can be like improved, this complexity can be improved to order of q plus log p using Fibonacci heaps, but in the worst case it will be order of q log p. Okay, and last but not least, we will have to compare between Kruskals and Prim's algorithm for our graphs. So which algorithm do we apply to find a minimum spanning tree for what particular graph? So when you have sparse graphs, that basically sparse means less number of vertices and less number of edges. So like not a really complex and dense graph. You apply Kruskal as compared to Prim's algorithm, because Kruskal really works well on sparse graphs and it has a better efficiency as compared to Prim. And for dense graphs, we prefer Prim compared to Kruskal's, because Prim's efficiency is really better than Kruskal's. Okay, so that is a analysis between Kruskals and Prim's algorithm. So yeah, that's it for this video. Hope you found it helpful. Check out the previous video on Kruskals algorithm, then you'll get more insight on the Kruskals particular algorithm, and check out the other videos in the video series if you want to gain more insight on graphs and networks. And I'll see you in the next video, guys. Make sure to like, share and subscribe if you found it helpful. Bye, see you.